Here we go, calculus friends. We're ready for related rates, example number 5. Again, try to get in the habit of reading the question ahead of time before you watch the video. But we're looking at example number 5. And again, we're talking about a sailboat coming in towards a dock. And so as we've been saying, it would be, in my opinion, very helpful to draw a picture here. And you're about to see my fantastic artistic abilities. So here's the water. And we have a sailboat, all right? Look at that. Oh man, that guy missed his calling. He should have been an artist. Here's the sailboat, all right? There's a dock, it mentions over here, that the sailboat's coming in for. Look at that. That's what you call abstract art. Now, it says that the sailboat, this is important, it's coming in towards the dock. And that'll dictate some of the numbers that we put in a little bit. And here's the really important part about this. It says it's coming in for the evening. And that really makes a big difference as to the mathematical setup it is. So here's the sun going down here. It's evening. Keep that in mind. That's very important. I'm kidding. All right. So anyway, why did I keep that in the question? I don't know. But anyway, whoever wrote this question, thank you for putting that very important information in there. And I digress. I apologize. All right. Now it says that there is a rope attached to the front of the boat. That's the bow, all right, the front of the boat. And this rope is attached to a pulley over here on the dock. So here's our pulley here. And this rope is coming in over the pulley. And apparently somebody is perhaps over here pulling that rope in to bring the boat in. As I said, I'm quite the artist. All right. And it also tells us that that pulley is 5 feet higher than the front of the boat. So let's put that 5 in there. And so here's the deal, and you'll get used to seeing this, and I gave you a homework one almost identical to this. But if you think about it, the idea would be that we have a triangle again here. If we assume that the pulley and this straight line to the boat form a 90-degree angle, and always remember this is one freeze frame of a video, so to speak, of this coming in towards the dock. So as this boat comes in towards the dock, wouldn't the length of the rope be changing all the time, and therefore it could be given a variable name like x, and then the distance from the boat to the dock is changing all the time, and that could be given a variable y. All right, now again, don't worry as to how you label them. As long as you stay with those labels consistently through the remainder of the question, you'll be fine. All right, so as this thing comes in, that triangle is changing all the time. But at every given instant, that triangle would follow the Pythagorean theorem, wouldn't it? So again, if you see a picture where you're dealing with a right triangle, just keep in mind that the Pythagorean relationship would probably be your base equation. So wouldn't that be 5 squared plus y squared equals x squared? And that's our base equation for this particular picture. And again, don't worry, if you had the x and the y labeled differently, just use those labels when you set it up. It doesn't matter. All right, part 2. What rate are we looking for? I see 2 potential questions. Are we looking for how fast y is changing or for how fast x is changing? And again, I always suggest writing that down. What rate of change do they want us to determine? And I can make a question where it would be either one, either the x or the y. But if you go back to the question, you'll notice it says, how fast is the boat docking? I interpret that to mean, how fast is the boat moving towards the dock? And would the distance between the boat and the dock be represented by y? I think so. Do you guys agree with that? Yes, we do, Mr. South Dakota. Thank you, students with the high-pitched voices. All right, so anyway, the distance between the boat and the dock would tell us how fast the boat is docking. So the way I have it labeled, that would be called dy dt. All right, if it said how fast is the rope being pulled, that would be dx dt. I think you get the idea. So anyway, this gives us the motivation, the impetus for idea number 3, differentiate with respect to time. So, by the way, let's go ahead and clean that up a little bit. 5 squared is 25. And this again would be our base equation, 25 plus y squared equals x squared. as I have them labeled. All right, so let's differentiate. With respect to time, God, that hurts every time I do that. Let's see. That's a constant, so its derivative would be 0, regardless of the variable. It's with respect to y in parentheses, quote unquote, air quotes, I don't know why, phantom parentheses. But if you do the chain rule to this, chain, right? Wouldn't you have 2y to the first, and then dy dt, remember the chain rule, outside, inside, equals, and then the same logic over here, that's going to give us 2x times dx dt, right? Power rule provides 2x inside with respect to t, dx dt. All right, idea number 4, substitute numbers and solve for the unknown. I want to remind you we're looking for dy dt, which is in here, and let's read the question and see if we can find numbers for everything else. Sounds like fun, huh? All right, so we go back to the question. Let's see, here we go. We already used the 5 when we set up our picture. It says that the rope is drawn in over the pulley at a rate of 2 feet per second. Well, wouldn't that be how fast the rope is shrinking? The change in x with respect to time. X is our rope. That's the speed at which, the rate at which the rope is being pulled in, otherwise known as dx dt. Look at the labels even. It says 2 feet per second, right? So that's 2. Oh, this is important. X is shrinking, the boat's coming in, the rope is getting shorter. That's a negative number. That's the change in x with respect to time, feet per second. It's shrinking by 2 feet per second. We heard you. Did you? Okay, good. All right, equals. Let's see what else we got here. How fast is the boat docking? That's the dy dt. When the length of rope from bow to pulley is 13 feet. Oh, at the instant when bow to pulley is 13 feet. At that freeze frame, 13. That'll go in for x. All right, and here again, dy dt is what we're looking for, so let's just transfer that down. Now the question becomes, what do we plug in for y? Well, here we go. If you look at this picture at this present time, you would hopefully say, oh, look, we have a right triangle. We know 2 of the 3 sides. I will say it again, this is only true for that instant when that was 13 feet. This is changing all the time, and we're only looking at it from that instant. So if we go ahead and apply the Pythagorean relationship to this triangle, we would then have 5 squared plus y squared equals 13 squared. I want to point this out. The original equation is relevant at any given time throughout the process. That's why we had the x and the y both in there. But at the instant when that x was 13, now we'll find the specific value of y, again, at that moment. So this is true all the time. This is true just at that instant. Anyway, continuing on. Hopefully we have a better marker here. 25 plus y squared equals 169. A little bit of algebra, subtract over the 25. It's just the algebra, right? And then square root both sides. And y technically is plus or minus 12. But again, given the physical nature of this question, we would ignore the minus. That's a 12, right? Okay, rates of change can be negative, but actual lengths, as in this case, that's what y represents. That's a 12. So, 12. Now it's just algebra. Solve this for dy dt. And again, I suppose I'll clean up some numbers as I do so. These are small enough. So that'd be 24 dy dt equals 26 times negative 2, negative 52, divide. Right? Okay, inside joke. All right. And dy dt would end up being approximately negative, let's go ahead and decimalize it. I understand some people would prefer the exact fraction. We can agree to disagree. How's that? There's bigger problems in the world to worry about besides that. Oh, and I can actually put a more exact, I see negative 2.16 repeating. Let's put a bar over that, then more exact, keeps everybody happy. All right. Oh wait, I forgot my units of measurement. Good thing I thought of that before we moved on. So the y is a distance, and I believe that the distances are mentioned in terms of feet. Good thing I caught that. Feet per, and then the time, again, is expressed in seconds. So at that given instant, when that rope was 13 feet, this was the change. This is how fast the boat was coming in towards the dock. And I'll point out it's negative because, again, the value of y is decreasing. It's shrinking. The boat's coming in. If, on the other hand, let's say the boat was going out, let's say in the morning, and again, that'd be a different picture, wouldn't it? But if that boat was going out, then wouldn't this have been a positive? X would be increasing, the rope would be getting longer, and that would have come out a positive number as well. So just pay attention to your positives and negatives when you look at these rates of change. Is the thing that you're measuring increasing or decreasing? I believe that's everything I can think of for example 5. I think I'm going to go now and find a boat. See you later.